Okay, did you decide? From the written, which ones would you like? 12? Okay, 12 for sure. What else? 12 and 14? Okay, so 10 was okay? You had to do 10, right? All right, so it sounds like 10 was good. So let's look at 12 and 14. Okay, so it says the airplane is flying with constant altitude and the speed 525 miles per hour in a direction of 25 degrees north of west, directly towards its final destination. Okay, so we know this is the idea of a vector because it's given us a speed and a direction for that speed. So this is going to be, we're going to draw a velocity vector. So 25 degrees north of west. So west is typically, conventionally to the left. So 25 degrees north of west might be something like that. Is that fair for 25 degrees north of west? It's in the ballpark. Okay? And so that's we know that's our angle. It's 25 degrees like that. And what's the magnitude of the vector? It's a velocity vector, so it's 525 miles per hour. So displacement vectors show you the starting point and the ending point. It's like change in position, right? So you've got the direction and how far they went. But a velocity vector is a different beast. It's kind of like this is occurring at one point in time. So like at a certain particular moment, that's the speed and that's the direction. So you have to see the difference between a velocity vector and a displacement vector. Again, a displacement vector, if this were a displacement vector, it'd be like would start there and ended there. Change in position, right? You started there, your change in x was this much, your change in y was this much, you ended there. Velocity vector is different. It's like in a moment of time, what's the speed and direction? Okay? If the pilot, okay, so then the airplane encounters a wind blowing a steady 33 miles per hour in the direction 80 degrees north of east. Okay, so then east would be this way, and 80 degrees north of east would be almost like this. And that wind is 33 miles per hour. Okay, if the pilot does not correct his course, at what speed and in what direction will the plane be traveling? So basically we have the speed of the airplane in its direction, and then it encounters a wind. So this is really just a matter of adding these two vectors together. You have this speed and this direction of the plane in terms of its heading and its motor, right, what it's doing, and then the wind comes in and will change the course of the plane this much. So we're just going to add these vectors together. When you add them together, you get the resultant speed and direction of the plane. Does that make sense? So how do we add vectors? Like we said on Monday, tip to tail. So I can take this this vector here, and I can just move it, because remember, vectors are mobile, right? Vectors are mobile. You can just move them around. So I can put it tip to tail like this. And then we want the net result of 525 miles per hour in this direction and 33 miles per hour in this direction. So our resultant, what we're looking for is that right there. Okay? So, and remember what we said on Monday. We said it's not quick and easy to add vectors in polar form. Polar form is not convenient for adding quickly, but what is? convenient for adding? Component form, right? So polar form, it's kind of like 525 that way, 33 that way. I don't know, right? I don't know. But if we had the x component of this of the plane airspeed, and then we had the x component of the wind speed, well, those are in the same direction, so we just add those straight up, right? And then if we had the y component of the airspeed of the plane and the y component of the airspeed of the wind, we can just add them up, because if they're in the same direction, you just add their magnitudes. So the question is, how do we get the x and y components of the airspeed vector? So I'll draw it again over here. And so anyone who's been paying attention in the last month or so of class, you should have an idea of how we can get this component, that's the x component, or the horizontal component, and then this component, and write this thing in component form. Has anybody learned anything? We've got an angle, and we've got this length right here of 525, so we're asking, how long is that? Should seem very familiar to conversations we had in the past. What's it about? Cosine, right? Cosine. So we want what? We know that the cosine of 25 would be this in the units of, if you thought of this as the radius of circle. So this is why we need trig to do vectors. Okay? So if you think of 525 as the radius of the circle, we know the cosine of 25 is just going to be this thing measured in the radius of the circle. So if we want this measured then in miles per hour, what do? Yeah, so cosine 25 is going to be what? This fraction of this radius length, right? Cosine 25 is a fraction of that radius length. That's our vector, original vector. And so if we want it in miles per hour, we want that fraction of 525. And remember, so this is, how can we get this measured in radius lengths? What's this measured in radius lengths right here? Sine theta, sine 25. Sine 25 is that vertical component measured in radius lengths, and that's a fraction of the radius. If we want it in miles per hour, that fraction of should feel very familiar. Should feel very familiar. So that gives us, so we can write then this, we can write r theta as, actually that's not actually what theta is. What is theta? $155? Okay, and so we can use cosine 25 and sine 25 and just make sure that we get the positive or negatives right. Okay, so what would this be? So we got 525 cosine 25. Positive or negative? Yeah. So if we keep our same positives to the right and positives up, then we could do negative 525 cosine 25, or we could have just done, what else could we have done there? Yeah, you just 525 cosine of 155, and then would we need to add the negative sign? No, because cosine of 155 would automatically give us that negative sign for us, because it's to the left of the vertical diameter. So either way, you could do negative 525 cosine 25, or you could do positive 525 times cosine 155. Okay, and then vertical component. So here, I could use sine 25. Would I need positive or negative? Just leave it. And what if I did 525 sine 155? Same thing, right? Because they both have the same, 25 degrees and 155 have the same positive value for sine. So you could do either way. You could do sine 155 or you do sine 25. Okay, what about the wind? So the wind, piece of cake. We're in the first quadrant, so there's nothing to think about here. This would be 33 cosine 80, right? 33 sine 80. So we're thinking about taking these fractions of 33. The fraction that it is of a radius to the right, that's cosine 80, so we want that fraction of 33. Sine 80 is our fraction of radius length up. So we take it by 33 to get miles per hour. So the wind then is, we could write it as 33 comma 80, and that's equal to 33 cosine 80, 33 sine 80, and so how do we get the actual speed and direction of the plane relative to the ground? Relative to the ground. What do we do? We've got this x-coordinate and this x-coordinate. So we're just going to add up x components. And that will be the resulting x component of the red vector here. And then we'll add up the y components. That'll be the y component of this vector. So let's actually get some values here. So I got negative 525 cos of, what is that, 25 over 360 times 2 pi. Plus 33 cosine of 80 over 360 . Okay, so I got the x component was negative 470. Confirm? Someone else get that? Okay, and then for y components, just take this. Got negative 525. Oh, this isn't working. Forget it. So we're going to have 525 sine of 80 over 360 plus 33 sine of 80 over 360, 549.5 for the y component. So that's the component version. That's the component version of our red resultant vector. So now the question is, what if we wanted now to revert back to the polar form of the red vector? So we know that .08 and 549.52 . So now the question is, how can we get the magnitude of that vector and the angle? So magnitude should be easy. What do we use to get the magnitude? Pythagorean theorem, right? It's a right triangle. Pythagorean theorem. What about the angle? Okay, so we've got, this is x component, or change, so it's change in x, right? We got a change in y of, remember in component form of a vector, those are not coordinates, right? They're a change in x and a change in y. Got to remember that. Why? Vectors are mobile, right? The location doesn't matter. It's specifying a change. And that's a really important thing to know about vectors. Okay, so now I've got the change in x and the change in y, and I want the angle. What relationship? Adam? Okay. Yeah, well, I asked you if it was right. Never said, yeah, it's right. Negative 445.9. Now is it right? So people told me the answer was right when I put it up there. This should be sine. Oh, I see. Yeah, this should be sine. And this should be cosine, and this should be. No, wait a sec. No, that's right. This is right now. No, it should be 80. That was right. The bottom left should be. This should be 25. Okay. Are we on the same page? How about now? Thank you. Okay. All right. So we got to change it here. Negative 470 was right. 254. It's a big difference. $254.4. Okay, so we got 470 to the west and 254.4 to the north. Those combined give this velocity vector. So Pythagorean theorem gets the magnitude, and so if we have change in y and change in x and what angle, what relationship or what do we have to do that? Help us get that. Tangent, right? So tangent of equals 254 opposite, or the slope, right? So we can think of it as slope, or we can think of it as opposite over adjacent. So we're talking about the arctangent. Okay, so remember, we said it briefly. What range of angles will arctangent come out in? What was our range of angles for arctangent? Do you remember? So when you put that in your calculator, you know what you're looking at. So we need every slope from negative infinity to positive infinity. So our range is negative pi over 2 to pi over 2. When you use arctangent on your calculator, you're going to get an angle between negative pi over 2 and pi over 2, and then based on your situation, you have to adjust. So when you do the arctangent of 254, so arctangent of 254.4 divided by 470.1, say, 0.496. What does this number mean? 0.496. So in just looking at the circle, what quadrant is that in? First, it's a first quadrant angle, 0.496. And what's the meaning of 0.496? What's its units? Is that degrees? No, that's radians. My calculator, I'm in radians. So I've got to convert that to degrees, and then that will be the same as. So really, I could have done, if I did negative, I could have done negative 470, but I should be able to interpret this. There we go. Okay, so yeah, think of this as a negative. So it's giving us the angle in the fourth quadrant. It's giving us this negative angle right there, negative 0.5, or negative, yeah, 0.496 radians. So that's going to be the same as the angle we want. What? North of west. North of west. So we need to convert that to degrees. Anyone got that in degrees? So divide by, no. Divide by 2 pi. Here. $28.42 degrees. Is that what you got, Matt?
Yes.
Thank you. So this negative 0.496 would be negative 28.421 degrees. So it would be that many degrees north of west. North of west. Okay, so it got a little messy up here. But here is the component form of that resultant velocity vector. So it'd be like the velocity of the plane relative to the ground. And then in polar form, use the Pythagorean theorem. We never found that, whatever that is. And then the angle would be 28.421 north of west. Okay, anybody have a question on this example? Does it make sense? Really, this is a really important example. It's got everything in it. Switching to component form, adding vectors, switching back from component form into polar form. All really important basic stuff for vectors. Are we good? Can I erase? Okay, let's look at 14. Okay, so let's just put this down here. So it says the piece of art is 30 pounds, hung from 2 wires as shown. Okay? Each wire supporting half of the weight of the picture. However, since the wires extend out at an angle, there's also 2 imparting force towards the left and the right. If one of the 2 wires were to snap, the picture would move towards the opposite wire. Therefore, the force on each wire is greater than 15 pounds. It's greater than 15 because to hold up the artwork, so what's the direction of the weight force on the artwork? So forget about the wires. If we were to draw a vector that showed the force of gravity on the artwork, which direction would it point? Straight down, right? Straight down would be, so we can just put that, maybe. So we can call that the weight force. It's going to go straight down. And so if that weight force is in component form, what would that be? Should all be able to write that in component form. What would that weight force be in component form? So what does this mean? This first is the change in x of that force vector. What's the change in x of the force vector? 0. P1 0. Agree with that? Yeah, there's no, it's all the change is in the y direction. What's the change in y? 30. Is that right? It's close. It's not 30. Negative, right? If we're in our system of positive is up, then a weight force is a negative force. The y direction is negative. So we could write that in component form as 0, negative 30. Does it make sense? And so that's why then the y components, if these are each at 20 degrees and symmetric and they're holding up then each of those wires is holding up 15 pounds of the artwork. And so that would be in the y component. So you have a y component 15 up and a y component 15 up of these wires. And since the wires are at an angle, that means you need a greater than 15 pounds in those wires to result in the vertical component being 15 pounds each. That's what they're saying. Okay, so what did they ask here? How do we know? I just explained that. Find the magnitude of ux and vx. Okay, so if we We just have to solve this triangle. So this is just solving trig. We've got an angle and the adjacent side. How can we find the opposite side? Yeah, you could use tangent. So say the magnitude of u, they're using double bars, the magnitude of ux divided by 15, opposite over adjacent equals tangent 20. So the magnitude 15 tangent 20. Anybody got it? Looks reasonable, right? If that's 15, that looks like about 5. 5 point what?
5.45. 5.46
pounds. Okay, so the x component of v would be positive 5.46. The x component of u would be negative 5.46. As vectors, right? So as component vectors, all right? Both of them are a magnitude of 5.46 pounds pointing in opposite directions. Total force in pound on each wire, piece of cake. So if this is, the magnitude of this is 5.46, how are we going to get the total force in pounds on this wire? Pythagorean theorem. That squared, 5.46 squared plus 15 squared would be that thing squared, square root.
15.96.
15.96. So the magnitude of u equals the magnitude of v equals 15.96. Part C, if the art weighs 80 pounds instead of 30, piece of cake. Suppose each wire can hold up to 50 pounds before breaking. What's the heaviest piece of art that can be supported? That's a nice question. So 50 pounds is the max here. So what's the heaviest piece of artwork that can be supported? What do we need to find that out? So if this can hold as much as 50 pounds, we're interested in that, right? How would we get the magnitude of that vector right there? It's a matter of what relationship? Cosine, right? Because you've got the hypotenuse and you want the adjacent side. You've got the hypotenuse there at 50 and you want the adjacent side that corresponds to 50 pounds. So it would be 50 times red. So tell me.
46.98.
So the artwork would have to be less than 47 pounds, right? What would it have to be?
Less than double that.
Right. So we've got two wires, right? Two wires that can hold 50 pounds. So we've got the 46.98 capacity on this one, 46.98 capacity on this one. So 46.94. So something like 47, like 94, just under 94, 93.5. Okay, questions? So this is easy. If we could change the configuration, what's the best configuration to get the heaviest piece of artwork? Then just holding so straight up and down, and then so you could do 100. If those were straight up and down, 50 on each side. Questions on this one? Does it help? You're shaking your head, Adam.
I was doing a different version of that. I wasn't using tangent, and I was finding the cosine of that, the x, and then using that to figure out what the hypotenuse.
You were kind of doing a roundabout way. Yeah. So that's the thing. So you can use a different relationship. It just may take you 2 steps instead of 1. Yeah. So it's basically just solving a right triangle, right? So when you've got component form, You've got angle and you've got a right triangle. It's just right. It's the trig, triangle trig, which we just did recently. Okay. Any questions? So we'll give you some more problems like these applications in WebWork. Okay. But we want to start a new. Talk about a new topic. Can you help me hand these out? Just go on this near side. Don't write on this yet. I need to just give you a brief intro. Just hold on to it for a sec. Yes.
Well, the last 3 topics we're going over.
Absolutely, yes. Okay, so we want to talk about something called the dot product. So we talked about addition of vectors. We know it's just as simple as having component form and adding the like components. What about multiplication of vectors? Thanks. Yes, thanks. So there's something called scalar multiplication. And so that's when you have a number, say 3 times the vector. So let's just say k. Okay, so think about like the force in the cable, okay? So you have a certain force in the cable, and that gives you a component vector of that force in the cable. And then we come along and we double that force, or we triple that force, so we take half of that force in the overall cable. What's going to happen to the components of the force in the cable? It should be pretty logical, right? So if here's our cable like this, and say it's like 3 and 7, so 3 pounds and 7 pounds, which makes some force in the overall force in that cable holding up the artwork. Now you're going to come along and you're going to put twice as much force in that cable. What's going to happen to the components? Yeah, so won't this triangle just be 2 times as big? And so your components will double too. So scalar multiplication is very easy. It's exactly what you think. If you multiply a vector by a scalar, you just multiply the components by that scalar. So that's one kind of multiplication in vectors. When you take a scalar, just a value, times a vector, you're just going to get that scalar times the components. And that should feel normal. That should feel reasonable. Okay, so the next type of multiplication is called dot product. So I'll just call it xy, but we know that, so that's, I don't know where a dot is on here. Oh, there we go. That's good. So even though I called it xy, we know the meaning of that is what? What are the meanings of these components? Change, right? Change in horizontal component, change in vertical component. Okay? So dot product is you actually multiply it's a way of multiplying two vectors together. Okay? And that gives you a number. It does not give you a third vector. It gives you a value. A scalar, I should say. So when it's dot product of two vectors, you get a scalar. And here's the scalar that you get. X times A plus Y times B. You multiply the like components, and then you add the result, and you get a value. So you're multiplying two vectors together. It gives you a number. So this sheet is about kind of trying to figure out what does that number mean. That's important. Really important. When you do that, when you take XA plus YB, you get a number. What does it mean relative to those two vectors that you started with? Why is that important? Okay, so here's what you're going to do. For the first 7 above the gray line, there's a thick gray line. For the first 7, you're first going to draw the two vectors with their tails at the origin. Okay? So like the first one. Let me pull it up. All right, I'll do how about the second one? So we're going to first start by drawing the vector, both vectors, each individual vectors with their tail to origin. So 5, 0 means a change of x of 5 and a change of y of 0. So you get that. 4, 3 means you change. Did I do 4? That's 4. Sorry. There we go. 4, 3 means change in x of 4, change in y of 3, and so you get this vector. So you're going to first draw those two vectors. And then you're going to compute the dot product according to this algorithm or this formula I just gave you. What will it be? 5 times 4 is 20 plus 0 times 3. 0 equals 20. Okay, so that's what that second one would look like. So what we're going to do is we're going to do a bunch of these, and then we're going to start seeing what pattern emerges. How does this number relate to those two vectors that we start with? So you're going to do the first 7, and we'll just circle around and make sure you get those first 7 right, because all the rest of them we're going to be looking back at those first 7 to try to figure this out. Okay, so just do the first 7. If you want to check with Jerome or I that you're doing it right. And then in a couple minutes, then we'll start doing the others and seeing if we can figure something out here. Okay? I'll take attendance. So Jerome will come around if you want to do a quick check. Okay, so you're going to finish this up for part of your homework for Friday is to finish this sheet up. On the back side, it looks like this, okay? What you're going to realize when you start doing all those ones below the gray line and start comparing them back up to the top is there's really 5 general cases of the relative directions of the two vectors. So we'll do one of them. One of those is the two vectors have the same direction. They point in the exact same direction. And what do you get for the dot product? How could you summarize what you get for the dot product when they have the exact same direction? Okay, but we want to be more general than that. Yes, so 25, yes. Why? Because each of these original vectors were what? Had a magnitude of 5. All of these vectors have a magnitude of 5, just so you know, right? If the components are 3 and 4, you've got 3, 4, 5 right triangle. So every vector has a magnitude of 5. So now, if the vectors have the same direction, in general, what would you get then? What are we seeing that you get for the dot product? How could you generalize that? Well, what if they had different magnitudes? So in this case, they all have magnitude 5. But what if they had different magnitudes? What would you say? Yeah, so it ends up being the product of their magnitudes. So when the vectors point in the same direction, what we're seeing is that the resulting dot product is like the product of their magnitudes. So after you get done with making all the graphs and comparing all those graphs at the bottom to the ones up top and we're going to think about you're going to come up with 4 other cases. Okay? 4 other cases for the relationship of the directions of A and B. And then a conclusion about the dot product in those cases. And then we want to look at these 5 situations and kind of come up with one general idea of what is the dot product. That's what our goal. So finish this sheet, and then there'll also be web work for Friday. Okay?